Okay, in this video I'm going to talk about how to find the tension of the Atwoods machine that we saw in the last example. In the last example we calculated the acceleration to be 3.33 meters per second squared using a 5 kilogram object and a 10 kilogram object. And we basically unraveled it like this and we said, okay, they share that acceleration. And we said there's a force of gravity from this one right here, but there's a bigger force of gravity from this one right here, and that's going to cause it to accelerate this way. But if I want to find the tension now, I can actually go back to the original diagram, and we're going to have to do something called an exploded free body diagram. An exploded free body diagram. So what does that mean? Well, what I'm going to do here is I'm going to take some of these ropes and I'm going to cut it. I'm going to do a cut. Let's do different cuts here. Let's do a cut around each of these guys just to show you what I mean. I'm going to do a cut around here, and I'm going to take that line and I'm going to make a dashed line just so you can see it like that, and I'm going to do different cuts on each of these. So I'm going to cut this one here, let's just say, and I'll cut this one here, just so you can see the different ways that we can look at this, because I don't need to cut this to find the acceleration, but if I want to find the tension, I do. So if I exploded that out, what I would get is this. If I clone this over like this, I'm going to get this. This object right here on the top is going to have forces coming like this. It's going to have force of tension down like this. And this is going to have force of tension down like this. But we don't really care about that. It shares the tension. There's a normal force up here that's holding this up. But that's what that one would look like if I cut it. This one here is going to be a little different. I'm going to have the force of tension like this, and I'm going to have that force of gravity this way. I'm going to have the force of tension up like this, and I'm going to have the force of gravity down like this of the 10. This is the force of gravity of the 5. So let's say I want to just isolate that system. I'm going to use this one just because the net force is going in that direction, and this one it would be going in the opposite direction because the red one's going up. So I'm going to take that one right here, that system with the green box, and I'm going to take that, I'm going to use that to find the tension. Okay, so I'm going to go like this. Let's see if I can just capture those. Bring that down here. Let's go down a little bit like this over here. So what I have now is I have a box. I have tension up, gravity down, like that, and I'm going to use Newton's second law again now. So I'm going to take this box here, I'm going to clone it like here. I'm going to erase these forces now. This is going to be my net force here. So what I'm going to have now is I'm going to say, well, I have my net force going down, which is just going to be MA net. Okay, and what I want to do is I want to find this tension here. So I'm going to define my positive y-axis going down, just because that's the direction of my net force. So this should always be in the direction of net force. Okay, so I'm going to say the sum of the forces in the y equals MA net. So my forces in the y, okay, I have this minus this gives me my net force. Does that make sense? Because this one is larger because it's moving down, right? So force of gravity 10 minus Ft equals MA net. Okay, so I'm going to solve for the force of tension here. Okay, what I'm going to do is I'm going to bring the tension over here and the MA net over here. So I'm going to end up with F of T is going to equal F, the force of gravity of that 10 kilogram object, minus MA net. So the force of tension is going to equal 10 times 10, because that's mg, right? That's mg, minus 10 times 3.33. Okay, so that's going to give me what? Well, tension is going to be 100, which is just the hanging mass, minus 10 times 3.3, so 33.3. So the force of tension is going to be roughly 60 66.7 newtons. Now notice the tension is actually less than the weight of the hanging object. So the tension of the object that's moving down, this one, is actually going to be less than the weight. The tension of the one moving up is going to be more than the weight. So if I use that 5 kilogram, I'd get the same exact thing going up. In fact, I can just prove that to you real quick if you want to see the red one. If I took that red one, took this cut here, I'll get the same answer either way. But it's a little more interesting because the actual tension in this case is going to be more than the weight. So let's say that I'm going to do another example over here. Let's do it, having trouble with this here. Let's do it over here in this case so you can see it side by side. So in this case, this one was actually moving up. So if I took that force like this, in this case the tension was greater because it's moving up, so it's greater, it's moving up like this, right? So this tension is greater like this, so this is my MA net like this. So if I said this time in this example, if I said my positive Y is going to be up now because my net force is up, I would say the sum of the forces in the Y equals MA net. They share the acceleration again, so now I'm going to say Ft minus Fg equals MA net, and I'm going to say Ft equals Fg plus MA net. This time I'm adding it. So you see that now that the tension is going to be more than the weight on this case. So it's going to be 5 times 10 plus, 5 times 10 plus 5 times 3.33. So that force of tension is going to be 50 plus 16.7 roughly. And that's going to give you the same answer no matter how you do it, 66.7 newtons. Now, the important thing to see on this side is that the tension is actually more than the weight. Remember, the weight here was just 50. Sorry, the weight, I'm going to do that in red. The weight here in this one was just 50, and the tension was more. On this one, the weight was 100, and the tension was less because it was accelerating down. So it just depends on which side you're on. So if you're on the side that's going up, the tension is going to be more. If you're on the side that's going down, the tension is actually going to be less. If this thing accelerated into free fall, the tension on this side would be 0, right? And the tension on this side would be even more because you would have to add up the accelerations, right? All right, so that's my example of the Atwoods machine. We did the acceleration, and now these are the tensions.